If I don't finish it within half an hour, I will continue in the last presentation. So again, we want to convert raw materials to products and we want to find the flow sheet. But now we are not going to do the evolutionary method and come to one final flow sheet. We will generate all possible flow sheets. So this is the hybrid enumeration and test. So here, just to tell you again, like a question was there also, thermodynamics and physical insights based on chemical process synthesis is presented, followed by extension of these ideas to group contribution method for flowsheet synthesis. On the right-hand side, you see a process flowsheet. After the first yellow box, which is the reactor, all the other yellow boxes are separation units. And the separation units are to separate the 4 compounds that are coming out of the reactor. So when we want to do synthesis, we need to ask, is there a reactor? Because if the same compounds come in and go out, then there is no reactor, like separation of crude oil into different products. And when the same compounds do not come in and go out, a new compound is added in the product stream, then there is a reactor and we need to give the reaction information. So after the reactor, we need to know also what is the minimum number of tasks that need to be done, processing steps. So that will be the number of products minus 1. So if there are 4 chemicals coming out and we want all 4 chemicals pure, then 4 minus 1 would be the minimum number that we need. And so the synthesis is, if we know this, that there is 1 reactor followed by at least 3 separation units, what is the best sequence of the separation units and what separation units there should be. Obviously, in this case that you see for methyl acetate, even though the minimum was 4, there are 8 processing steps needed. So is that the best way to do it? One can question. So what we will propose is that once we get a mixture and we get a problem definition, we will try to identify the mixture. We will try to identify any isotopes are formed or not because they affect the separation. And then for every binary pair of compounds in the mixture, so if there are 3 compounds, then there are 3 binary pairs. If there are 4 compounds, then there are 6 binary pairs. If there are 5 compounds, there are 10 binary pairs, and so on. So we can find out how many binary pairs are there, and for each binary pair, we can extract the pure compound property of the compounds and look at the ratio of the properties. Why this ratio is important? Because every separation technique is exploiting one of the differences of those properties. Like distillation is exploiting the difference in boiling point or vapor pressure. Liquid-liquid extraction is looking at the solubility. Membrane is looking at the molar volume. Pressure swing distillation is looking at the whether the isotope changes with pressure or not. So each of those binary ratio of properties tell us or give us an indication of which separation technique could be used and whether it would be easy or difficult. If the value is close to 1, it will be difficult. If the value is greater than 1, it would be easy. If the value is close to 1, let's say for boiling point or vapor pressure, that would indicate that vapor liquid separation would be difficult and solvent would be needed. So if solvent is needed, we need to design or find a solvent, select a solvent. We need methods to calculate the solubility, selectivity, and so on, and so that we can find the solvent. We could also go and search in the database if all the data is there. So that problem needs to be solved. And then once we have all this information, we can say for every binary pair, what are the feasible separation techniques available? And if we find them, how do we combine them to get a flow sheet? So that's the combination rule that we need to work on to generate a flow sheet. So that's why this method is called enumeration and test. We can easily generate all the flow sheets based on what are the feasible separation techniques, assuming that there is only one reactor. If there are more than one reactor, then we can also do that. And there will be more than one reactor if there is more than one catalyst. That means if catalyst A is there to do the reaction, we have one reactor. There is catalyst B, there is another reactor. So then we can find out which combination of reactor and separators will give us the best flow sheet. And then we need to generate all the flow sheets and then screen them according to objective function and performance criteria. So now we come to the group contribution method. And I will explain the theory for group contribution method and how this can be applied to flow sheet synthesis. As you may know from property prediction, what you see are groups of atoms, like one atom and 3 hydrogen, and that has a free bond, or 1 carbon and 2 hydrogen, that has 2 free bonds, or 1 oxygen, 1 hydrogen, that has 1 free bond. So these are groups of atoms. Now, in a molecule, we know that there should not be any free bonds. So we can try to find out ways to combine those groups to form chemically feasible molecules like you see here. The requirement is that there should not be any free bonds and the valency requirements of the atoms are satisfied and so on. So if we can get a computer to do it, it can be very fast because by the time we maybe generate 5 to 10 of these molecules, the computer will generate thousands of it. So can we use this idea to generate flow sheets then? So then what we will do, before I go there, we can say that also, as soon as we have identified which groups represent a molecule, then we can use this property function that you see below, through which the number of groups and their summation of contribution gives the property. So group C is a first order group, D is second order, E is third order, F is a correction. So if we know how many first order groups are needed, for example, in ethanol, and what is the contribution of each of those to boiling point, we can use this simple summation to calculate the boiling point. So like that, if we have a wide range of properties, actually we have just published a paper with 25 different properties like this, so we can immediately calculate 25 different properties. So that's very powerful, very simple, very easy, and relatively accurate, plus minus 10%. Can we use this idea for process synthesis? So let's say then how we will do in process synthesis. We have the groups, we generate the molecules by combining the groups according to the connectivity rules. And once we have generated the molecule, we calculate the property from the group contribution. So now if we say that similar to the process atom group, if we have a process group, and you will see what a process group is, can we also then combine the process groups to give a flow sheet according to some connectivity rules? And then if we also have some property models, like the group contribution property model of a molecule, can we then also calculate the properties of the flow sheet? Then we do not need any simulation at this stage, up to this point. So let's see what a process group would be. So a reactor, a process group, reactor process group has an input, which is 2 compounds, A and B, and an output, which is 4 compounds, A, B, C, D. So this is a A plus B going to C plus D, no inert. So that immediately tells us that this is a reactor group. And how will a reactor group be connected to others? If we want to separate a reactor exit of a reactor group, A, B, C, D, any separator unit that handles 4 compounds can take this and connect to it, to the reactor group. So here is a separation. I'm only showing here 2 compound. So if we have a 2 compound feed, that gives us 2 pure product, B and C. And the rule is that if we have only a single compound in an exit stream, there's nothing more to separate. As long as the stream has more than 1 compound, we need to separate. So then we know where is the end point, and that's why when there is 1 compound, we say that that's the outlet stream. We cannot do any more processing on that. If the pair of AB, that is 2 compounds, form an azeotrope, then we cannot get pure A and pure B, as you can see there, because azeotrope will be AB, and we will get a pure A or a pure B. Then if the azeotrope changes with pressure, we have a pressure swing distillation process group. Just like an aromatic ring, this could be a process group like that. So like this, we can generate all kinds of process groups with membranes, with 3 compound distillation, with 4 compound distillation, and so on. And so that you can see that at the top, we have a flow sheet with 2 feed going to a reactor, then 4 compounds go to a flash. Out of the flash, 3 compounds liquid go to a distillation. 1 compound, which is the reactant, is identified and sent back. And from the distillation, the bottom product is B, which is a reactant, identified and sent back. And CD goes into a next separator, and membrane is found to be better. So a membrane is used. And after CD, nothing else is needed. So we have 2 input groups. We have 1 reactor group. We have 3 separation groups. And we have 2 outlet groups. So we put those groups in there, and we have a representation of the flow sheet in terms of groups. Okay, so the next step, how do we generate alternatives? If for the separation of 4 compounds, we have flash, but we have also other way to separate 4 compounds, and other way to separate 3 compounds, and other way to separate 2 compounds, then we generate all kinds of flow sheets. So this is the list would be that we will find out how many process groups we have for each of those steps, for compound separation, 3 compound separation, 2 compound separation, and then we can enumerate by combining, making all the possible combinations. So again, this is what I'm saying, that if we have 1 reactor, which is A, B, C, D, and then we need separators. So we need separators that separate 4 compounds. We need separators that separate 3 compounds. We need separators that separate 2 compounds. And they are positioned after the number of compounds have decreased. And then if we have a set of groups, which you will see soon, then we would be able to generate all kinds of flow sheets that we did in terms of molecules. Also, we can put some advanced information about the groups. Some of them, like gas membrane, process group handles a feed which is vapor. Liquid membrane handles a feed which is liquid. Distillation can handle vapor liquid or vapor liquid, molecular sieve liquid, and so on. So this kind of information we can already put into the system. So the system can choose, for example, which of those streams will be connected to a process group. And then comes the question of how do we calculate the property? Because if we want to calculate energy consumption, we will need to do a process simulation. But we have not generated the flow sheet, and we do not know any of the design parameters. So how do we calculate the energy consumption? What we have done is that for every process group, you can see POSK is a process group, and A is the contribution to a property, like the energy index. So if we know how many process groups are in a flow sheet, and if we have the value of A, we can very quickly calculate the energy required by that flow sheet. And we can also do the carbon footprint, and we can also do the product recovery. Then the question is, how do we get the value of A? It is exactly the same way as we develop property group contribution based property model. We collect data of hundreds of molecules and their property values like boiling point, and then we find out the contribution of each group to the molecule and for the property. So like this, we have generated hundreds of data points for distillation with 2 compounds, 3 compounds, 4 compounds, and then use that data to back calculate out to regress this parameter. So this parameter is not totally just A. It also has a P and a D. D is actually the driving force. The driving force is the difference between the vapor composition and the liquid composition. And you will see in tomorrow's lecture, if the driving force is large, then the energy is small required, is inversely proportional to the energy required. So, and P is the position of the group, because if we put a easy to separate group afterwards, then there is a penalty. Easy separation should be done first. That's the rule. So we put those kind of things into account. So P takes care of that. The easiest, the group with the largest driving force should be the first, the easiest separation, and then the next, and then the next, like that. So giving all this topological information into the groups and the flow and the structure, we have regressed the parameter. So for any flow sheet, we will know P, we will know D, we have the regress parameter A, we can easily calculate the energy index. Okay, no flow sheet simulation is needed, no design is needed at that stage. And similarly, we can look at the product recovery based on the separation factors, and the energy that we have calculated also helps us to calculate the carbon footprint. So all of these are group contribution. So we have a good way of ranking the flow sheet immediately after we generate. No flow sheet simulation. Now let's go through the methods. I will only explain steps 1 to 5 because 6 and 7 are related to design and simulation, which will be tomorrow. So first we define how many compounds are coming in, how many products are going out, what are the chemicals, all of these things. So that's the problem definition. We need to give the chemical system, we need to give the process topology in terms of inlet and outlet information, and we need to give the reaction. We are working on developing a reaction database that will automatically put the reactions, but at this moment we need to give the reaction. That is all the information one is needing. Then having the information, the system, you will see the demonstration of it in the last session through ProCFD. It will extract all the data for every chemical compound, all the pure compound property, the molecular structure, the groups, all of those things. For the properties that are there, it will extract from the database. For the other properties, it will calculate the properties so that phase behavior can be calculated, azeotrope formation can be calculated, and so on. And based on this, it will give us information about how many binary pairs are there, which forms an azeotrope, what is the binary ratio matrix value for different properties. So you can see an example like this. Here is a table. for every binary pair A, B, C, and so on, and properties, it will give the ratio. As I said, if the ratio is close to 1, it's difficult for that separation. If the ratio is greater and does not form an isotrope, it is easier. And so in this case, 2.5 is the ratio for vapor pressure. So A and B can be separated by distillation if they do not form an isotrope. So like this, we will find out for the entire set, for every binary pair, what is the separation and which are the separation techniques that can be used. So in that case, we will have a very large table through which we can generate all possible alternatives. So the next step is, if we have the binary ratios, then we have a knowledge base that tells if for the binary ratio and for the corresponding property, the value is between this range or this range or this range, then these are the feasible separation techniques. So through that table and the knowledge base, we can identify all the separation techniques. And here is an example. What it says is that there is a possible separation of B and C. There is a possible separation of ABC, ABCD, ABCDE. So for each of those separation of compounds, we have the corresponding process groups. And then the structure of the superstructure is what you see in the diagram on the right-hand side. We have coming out, or let's say input, 4 compounds. This could be coming out of a reactor or just the separation problem. Then at the first stage, we want to separate 4 compounds, then 3 compounds, then 2 compounds, and then 1. And we can work out all possible combinations as soon as we have this. And as soon as we have this, we also generate what is called a S file. An S file is similar to the SMILES of a molecule. With the SMILES information, we know the molecular structure, we can draw the molecule, we know the process groups needed. Sorry, atomic groups needed. With S file, we will know the process groups that are needed, and we will be able to draw the flow sheet. So here is then flow sheet that is doing a reaction followed by separation and recycling the reactant A and B. And then at the bottom, you see the S file. It starts with IA, that is the input of the main reactant. Then the reaction, AB is the reactant, ABCD are the products. Then it says that there is a second reactant, which is B, so that it knows that A and B has to be recycled. And then the first separation is a gas membrane, which will remove D, and then distillation, which will remove A as a product, and then distillation, which will remove B and C. And then since every product, single compound has O, then this is a product. If it is A, it will recycle back. So that's the S file, and we have a program that from the S file, it will generate the flow sheet. Sorry, represent the flow sheet. It will generate with the combination rules. So I've already talked about this. Let me go. And there are different mixers and reactors and splitters in terms of how many streams they may have. We can give those things. Sorry, and then we don't go to step 6 now because we will talk about it tomorrow. So I will skip this once. And we also have a list of every process group, what kind of specifications are needed to be able to do a process simulation. These will be used tomorrow, so I will not go through it now. And then I will briefly go through an example, and you will see the example for HDA later on as part of the software. Here is the methanol plus acetic acid gives methyl acetate and water. We have all the information. We need to find the nature of the mixture, the state of the components of the reference at the reference condition, the number of binary pairs, analysis of the isotopes, miscibility, and so on. So we find out that there are 6 binary pairs, 3 of them form isotope, and 2 of them, the isotope is pressure dependent. So this is very important information. We collect it, and also we see at the boiling points and melting points whether each of the compounds will be liquid or vapor or solid. We do the mutual solubility calculations in case one of the compounds can serve as a solvent for the others. We check also the solubility parameter based on our calculation and database, and they look quite good. We look at whether carbon dioxide could be used as a supercritical solvent. So that also can be done. And then here is a binary ratio matrix. So the columns are, in this case, the columns are the binary ratios. There are 6 binary pairs, and the rows are the different properties. And then based on these, we find out from our knowledge base what are the separation techniques. So for every binary pair, it tells us with on the column, the second column, which are the feasible separation techniques. And the ones that are bold, it says these are better than the ones that are not bold. So now with this information, we can actually generate the entire superstructure and generate all possible flow sheets. So then I will show you how we generate the flow sheet. We have the reactor. We know 4 compounds go out. Then we have different separation techniques available: S1, S2, S3, S4, S5. And then the question is, how do we combine them to get one flow sheet? So this is one example of a flow sheet. Is this the best? We have to do the calculation. So we do the ranking without doing the simulation. We find out in terms of energy, which is the lowest in terms of carbon footprint and product recovery. So we can do that without simulation, and then we can say we will take the top 5, and for those we will do the detailed simulation and so on. But that is the design part. We stop with the synthesis part at this point. And so also you will see that this kind of the flow sheet that I've shown you here is actually better than the initial flow sheet that I showed initially with the yellow boxes. They had 8 separation units. There are not 8 distillation columns here, and it is possible to reduce much more, which I will show in webinar 1.3 on 16 July. I will not go through the other examples that we will share all the presentation files afterwards, so you can look at in the same way a bioethanol production process has been generated, not just one flow sheet, but many alternative flow sheets. So with that, I will stop now, and if there are any questions, I can take very briefly 1 or 2 questions, and then afterwards we can take the other questions. So are there any questions?
And if you have any question, please use the raise hand button.
Okay, one person has asked why the mixture type and the azeotrope is placed in the first column. The reason why the mixture type and the azeotrope is placed in the first column, actually the mixture type is the first. From the mixture type, we generate all the binary pairs, and we calculate all the binary pairs with respect to the binary ratio matrix. The azeotrope, even though it was in the first column, it was much lower in the rows. So it comes afterwards, that after we have done the calculation for the binary ratio matrix, then we will do the azeotrope calculation. Because if the binary ratio says that distillation is possible, then we need to check whether they form an azeotrope or not. If they form an azeotrope, then it is not helpful if the ratio is high. But if the ratio is high and there is no azeotrope, then distillation is good. So I hope I answered your question. Participant 103. Maybe this was a question from before. Somebody had asked, XD is a vector of all distillation components, then no. Because in a distillation column with one feed and two products, one specification can be given at the top, one specification at the bottom. So it is one product recovery at the top, one at the bottom. And if it is the separation based on the binary pair, we suggest to use those two pairs as the key compounds to give the recoveries for them.
Another question, how the methodologies will work for batch process synthesis?
Yes, we have a separate method for batch process. The separation requirement is the same, only the difference is what will be the batch operation time needed to perform the separation. So we have a different method to calculate for the batch sequencing. Any more? You can keep your questions. Afterwards, we have the second one after Professor Grossman's presentation. And then we will see the demonstration. Maybe you will have more questions at that time. Okay, so Orakoch, you will now, I will stop sharing and you will now need to start the recorded lecture.
Okay, sure.